All right, welcome to AP Practice 2011, number 2. So this was the third one that was requested. I'm happy to get into it with you guys. In this situation, it says an amusement park ride is features a passenger compartment of mass M that is released from rest at point A as shown in the figure above and moves along a track to point E. The compartment is in free fall between A and B, a distance of 3/4 r, then moves along a circular arc of radius r between B and D. Assume the track is frictionless from A to D and the dimensions of the passenger compartment are negligible in comparison to R. Fantastic. It says on the dot, draw the forces. So here's A, and then it has for you in A a dot, and it says put some forces on. All right, we can handle that. Well, we know obviously the Earth is going to pull it down. That's the weight, we call that mg. And then there has to be a perpendicular force provided by the surface. Even though the surface itself is curved, it still provides a perpendicular force. And we call that one the normal. There you go. I think that's it. Let me check the rubric. 2 points. 1 for each force. Nice and easy. +1 for this guy, +1 for this guy. All right, let's look at B. Now, B tripped up a bunch of people, and I can understand why. And I think what we're going to have to do is we're going to have to draw a picture that makes a little bit more sense here to be able to do this. So I'm going to not draw on here because you can't add anything to your diagram. So I'm going to redraw this here and see if we can't do a little bit of geometry. That's not going to help. Let me do it another way. I'm going to make it a little steeper on purpose. I think if we make it steeper on purpose, we're going to be able to see what we're looking for a little more clearly. I know that's a little steeper, but it's easier if we do it this way. So we know that the Earth pulls it down. That's the weight. We're going to put that here. And we know there's a normal force here, perpendicular. And so B says, what we want to do is we want to write a statement for the centripetal force. So I know the centripetal force is the net force that points toward the center. Now, if you're in uniform circular motion, then it's just the net force. But this is not in uniform circular motion because it's speeding up through here. So it can't be just the normal. It has to be some combination. So if you look at this over here, if I look at the components, I can see that the centripetal force is the difference between these two. So it's going to be the normal minus whatever this component is here. And what we have to try to do is we have to try to figure out, is that component mg sine theta or mg cosine theta? So let's look a little bit closer at this diagram here. We're going to have to relate it to this diagram here. If I draw this horizontal relative to the board here, it intersects that. And the diagram gives you theta right there. So I'm going to say that that is the same theta. Because this is along this axis there. So that's theta. Which means that this one would also be theta. Which means that this would be theta. But what that leaves you with is this one is not theta, that one is phi, and this one down here is theta. So given the construct of this, this has to be 90. These two together have to be 90, just like those, so this is theta. So it turns out that this component here is mg sine theta. I know that that is a little confusing, and a bunch of you had cosine because I think you tried to overthink it a little bit. Some of you didn't think enough and kind of guessed the right answer. Either way, it doesn't matter to me. The centripetal force is the normal force minus mg sine theta. And it was actually supposed to be a really easy problem because it was just a quick one-pointer. Let's look at C real fast. C says, derive an expression for the speed of the passenger car as it reaches point D. No problem. So you're trying to find the speed along a circular or along a curved track. This seems like an energy problem to me. So let's look at it as an energy problem. I know that the initial energy has to be equal to the final energy. So when I look at the initial energy, it's all gravitational potential, and it goes to all kinetic. No rotating or anything here. This one's pretty straightforward. So I have mgh is equal to 1/2 mv squared. And we need to drive an expression for the speed, vd, as it reaches the bottom. So the thing here is you kind of just got to look at the diagram and see, like, well, what are we talking about here? What is the height? So the height is going to be this distance here, which to me is 3/4 r plus r. So mg r plus r is equal to 1/2 mv at d squared. M's magically disappear. This is 7r over 4. So 7r over 4 is equal to 1/2 mv at d squared. And as I go, oh, this m disappeared, sorry. Got a little distracted there. And I see I can multiply both sides here, and I end up with 14 over 4, which is 7 over 2 rg square root is equal to v at d. If I take a look at the scoring on this one, this is a quick 2 points. For applying the kinetic energy equal to this, you get 1 point here, and then for the correct answer, you get another point, quick 2 points. All right, let's look at D. D says a force acts on the compartment between points D and E, bringing it to a stop. If the compartment is brought to rest by friction, calculate the numerical value for the coefficient of friction, mu, between the compartment and the track. All right, so we're going to need this here, because I think we're going to need the initial velocity. So let's leave that here, but let's get rid of the other stuff. Because there's 2 ways to do this one. One is going to help us later on. The other is a pretty easy energy, a way to represent this with energy. So let's look at D. Let's do the energy one first because I think it's pretty easy. If it's moving at D and stopped at E, what I know is that all the kinetic energy goes to the work done by friction. That's where the thermal energy is generated, no big deal. So we start with the kinetic energy at D, so it's 1/2 mv at d squared, and the work done by friction is equal to the frictional force times the slide distance. And that's nice and easy because as it's sliding across here, these two are opposite one another, so we end up with a negative work, which is good for us. I know that the frictional force is equal to mu n times d. But in this case, if you looked at the force diagram for your box as it's sliding, we know that friction, normal. So in this case, because there's no vertical acceleration, the normal force is equal to the weight. And I start with the kinetic energy here, 1/2 m via d squared. And so now I'm looking for mu. So we can see the m's are going to disappear. I have the v, I'm looking for the mu, I have g. I look at the diagram, the d is 3r, and I know that the via d is this, so let's plug in what we know. 1/2. Now this is via d squared, this is the square root, so I'm going to get rid of it. 7/2 rg is equal to mu g, and the d that it slides is 3r. So r's can disappear, g's can disappear. So on the left side, I just have 7/2 divided by 2, and I'm also going to divide by a 3 here. So I end up with mu is equal to 7/12. So that's one way to do it, and that's a pretty powerful way to do it. Let's look at the other way to do it. So this is D the other way. If you look at D the other way, I know that it's sliding and being brought to a stop by friction. I can actually use Newton's second law. So if I start with a Newton's second law statement, the net force is equal to the mass times the acceleration. The net force is equal to, well, in this case, it's just the friction. But the friction is the coefficient of friction times the normal. And again, we see that that's equal to mu mg. So if I set these two equal to each other, ma is equal to mu mg, a is equal to mu g. If I think about this equation, v squared is equal to v0 squared plus 2a delta x, I can substitute my acceleration in here. My delta x is the actual d, which is 3r. It slows to a stop, so the final velocity is 0, and the initial velocity is right here. So I can actually solve for everything that I need here. So 0 is equal to, again, this is squared, so I'm going to get rid of the square root, 7/2 rg plus 2 times, and this is where it's a little tricky because it's moving to the right, so the velocities are positive, so the acceleration is negative, so I'm going to put in negative mu g here. And this is 3r. I'm going to come up here to finish. I'm going to subtract this from both sides, so negative 7/2 rg is equal to negative 2 mu g times 3r. Okay, we can get the negatives to go away. We can get the g's to go away, we can get the r's to go away. And what you'll notice here is this is 6 here. If I divide both sides by 6, I end up with mu is equal to 7/12. So it really doesn't matter which way you do it, we end up with the same answer, which means that we're probably on the right track. So this section here, the way we did this with F equals ma, and the net force is the mass times acceleration, the net force is the friction. It actually turns out here that this is really negative, right? Because we end up having to use it negative down here, which makes the acceleration negative. That might be important in a moment. If I go to look at the points on this bad boy, pause a second, hold on. If I look at the points on this one, this is a 3-pointer. So if you use the work energy approach, you get 1 point for this, You get 1 point for the correct frictional force expression and then 1 point for the answer. If you do the kinematics approach, you get 1 point for applying Newton's second law, 1 point for applying the correct velocity equation, and 1 point for the answer. This is not 6, it's 3 or 3. All right, let's look at the next part. The next part's the hard part. So this is E, and E is pretty extensive. Okay, we're going to get rid of all this so we can do it all in one shot here. So EI says, in this case, we have our guy and he's cruising along here, but now consider a case where there's no friction between the compartment and the track, but instead there's a braking force, which is negative kV, where V is the velocity. So this time, as it's cruising across here, if we look at the force diagram for it, it's moving to the right. We would have the weight again, the normal force again, but this time your force is kV, small k, and because it's left, it's negative. And what this says is that your force that's bringing you to a stop is dependent upon the velocity. More velocity would give you more force. So it says, write but do not, so this is EI, it says, write but do not solve the differential equation. No problem. It all starts with the net force. So what do we know about the net force? It's equal to MA. Given this diagram, how do you express the net force? Well, the net force here is negative kV. So I'm going to set these two things equal to each other. MA is equal to negative kV. But what do we know about acceleration? The acceleration is the derivative of the velocity with respect to time. If I substitute this in here, I end up with m dv dt is equal to negative kV. So this is a problem because you have a v on one side and a v on the other, but they're not like terms. So this is why it's a differential equation, because you have the same variable. And then, so this is good for the answer here. It says write but do not solve. This is it right here. You could also write it dv over dt is equal to negative k over mv. Does the same. So that is EI. Okay, that is EI. E double I says, once you have your equation, what we want you to do is we want you to now actually solve it. So for you calculus fans out there, you should be able to write and solve. If you're not a calculus student, you definitely should be able to write to get to here, because there's nothing, but the solving would probably be a little too hard for you right now, especially because we weren't able to train for it in the classroom. So to do this, the first thing you're going to do, okay, the first thing you're going to do is you're going to separate your variables. Let me get all the v's on one side. So if I divide both sides by v and multiply both sides by dt, I have 1 over v times dv is equal to negative k over m dt. But what we have here is we have a derivative, and so if I want to undo the derivative, I'm going to take the antiderivative of both sides. So the antiderivative of 1 over v dv is equal to antiderivative negative k over m dt. So if I apply this, I'm going to bring this up here. The antiderivative of 1 over v dv turns out to actually be the natural log of v. And then the antiderivative of dt is just t, so negative k over m t. But you have to add c to all of this. And that's because when you take an antiderivative, you need this constant here because you lose the initial value. I want to solve for v for not the natural log of v. So the trick we use is we have to undo the natural log, which means we're going to take e raised to the natural log of v. But I got to do it to both sides. E raised to the negative kt over m plus c. These undo each other, and this gives me my v that I'm looking for. This gets a little tricky over here. So I'm going to take e to the natural log kt over m times e raised to the c. Remember like back in like freshman year when you learned if you have two bases here, if you multiply the bases you can add the powers together? Well, I just undid that. So here we were adding the powers together, but what it is, I brought it back the other direction, now I'm multiplying the bases. The funny thing about this is that e raised to the c is just a c. It's just a constant. And so when I rewrite this, I'm going to take this as a new constant times e raised to the negative kt over m. So what does this represent though? Well, one way to think about this is if I put a 0 in for time, 0 times k divided by m makes that whole thing 0. E raised to 0 is basically 1. So this constant here is actually the initial velocity. It's the velocity at time 0. So v0 e negative kt over m. And that is the answer to the differential equation. The last part here says, it says, on the axis below, draw a graph of the magnitude of the acceleration versus time. So magnitude means they don't want it positive or negative, they just want you to graph the value. So if we just go back and look at our graph, or look at our initial situation, as it's sliding here, it's slowing down. But what's happening to the acceleration? Well, the acceleration itself is related to the velocity. So as the velocity decreases, the acceleration also decreases. So we should have a graph that's going in this direction, but it can't just go down like this because it can't cross over. So maybe it decreases asymptotically, but it starts with some value because when it hits D, it's already moving, so it's going to have some acceleration and velocity, and then asymptotically decrease, getting closer and closer to 0. And the thing is, what we want to find is we want to find this value right here. Well, what do we know? We know the acceleration is the antiderivative of the velocity with respect to time. So can I take the derivative of this statement, is the question. Again, you'd have to be a calculus student to be able to do this effectively, but to take the antiderivative of this, this is a constant, and so you have to apply the chain rule. The derivative of e to the negative kt over m is kt over m. It's e kt over m, and then apply the chain rule. You got to multiply that by front, so v0 times kt over m e kt over m. This would be negative, but they only want the magnitude. At time 0, this is 0, makes this whole thing 1, and so the acceleration at time 0 is v0 kt over m. So that would be this value right there. If we look at the scoring rubric for this one, in A it says for writing this you have +1, and for writing this you have +1. So if you know Newton's second law and you apply the derivative effectively. That's 2 points. E2 says for separating the variables, so getting all your v's on one side, you get a point. And then for doing the calculus, you get another point. And then over here, there are 3 points. You get 3 points. One for getting the correct value here. One for asymptotically approaching. And then one for concave down. So the graph was 3 points. And that's 2011 number 2.